All right. So let's say you have the ground right here, and you have maybe a table right there. There's your table. Okay. And you have a pulley. There's your pulley. Okay. Well, that's kind of in the wrong spot. Should be like over there. So you have a pulley, and then you have a mast hanging on this side. That's kind of in the wrong spot. Let me move it over a little. Then you have another mast. You have a rope here going this way as well. Again, that rope should be maybe up a little. There, that looks pretty nice. And actually, I'm going to move this. I'm going to make my table taller. Okay. There we go. Oops. Haha. All right, there we are. There's my table. There's the other leg of my table. Okay. And I got mass A and B. Okay. Here's mass A, let's say. Here's mass B. They don't have to be the same mass, and let's pretend we don't know the masses. Okay. So I'm going to say I don't know the mass of A or the mass of B. All right, I'm just going to call this object A, object B, and let's see what we can figure out. Okay. Shorten this a little bit. Nah, I don't want to shorten that. That's fine. Actually, I don't even need that. I'm going to get rid of it. Okay. And now all this stuff's like too big. Whoops. Try that again. So I'm gonna move all this over here, group it together, make it much smaller. There. That looks pretty good. So let's do our force diagram for object A. Okay? I'm gonna move this down a little bit. So I'll make the force diagram for object A right above object A. And object A is my system. Okay? So I got weight of object A. I've got normal due to surface acting up on object A. I got tension to the right acting on object A. All right? For system B, I've got weight going down, and I've got tension going up. Okay? So, let me move that one over. Whoops, I don't want to do that. Let me fix that one. That one's messed up. So, there's my tension. All right? And there's system B. Okay? I should probably do vector sum diagram for each of these. Let's take my forces. I've got weight going down. I've got tension going to the right. That's a little too long. Shouldn't be quite that long. Fix that one. So I got tension to the right. That looks about right. And I've got my normal going up. So normal, weight, tension, and this is the weight of object A, right? And then my net force vector, my sum of these three vectors, when I add them as vectors, it has to have this length here that's exactly equal to my tension. So basically that blue vector I drew is equal in magnitude to my tension, and that blue vector is what I get when I add the weight vector, the tension vector, and the normal force vector. So if second law is true, then I can just write, oh, okay, this is my net force vector. Well, that means this is the mass of object A times its acceleration. So I'm using second law to replace my net force vector's magnitude with its acceleration scaled by its mass. Okay? So MA is what I'm replacing the net force with. Now, if I go to my hanging mass, which is mass B, and I do my vector sum diagram there, I get something like this, right? I get the weight of object B going down, tension going up, and then what you'll see is its net force vector will be going down, right? And that means that mass of object B times its acceleration will be that net force vector. That net force vector's magnitude is equal to MVA, right? So this vector here has a magnitude of mass of B times acceleration. Okay, so there's my force diagrams and my vector sum diagrams. Now I'm going to just use these diagrams to develop equations that are expressing the relationship between the magnitudes of my vectors. So I'm not going to worry about the direction of my vectors. I'm just going to worry about their lengths. And from system A, I can easily see that like tension has the same magnitude of MA for system A. So tension has the same magnitude of mass of object A times its acceleration. All right. This is a little trickier. The tension acting on system B, which is the same tension that's acting on system A, same rope, that tension has to be equal to, so that magnitude, the magnitude of that tension has to be the magnitude of the weight vector minus the magnitude of the net force vector, right? So again, there's a couple ways you could say this. I'll say it a different way just for fun. The length of my weight vector here has to equal the length of my MA vector plus the length of my tension, right? So my preference is to solve for tension because I'm going to want it in that form. Tension for system B is going to be the length of the weight vector minus the length of the MA vector, or the net force vector. Same thing. All right? So the magnitude of the tension, the length of the tension vector equals the magnitude of the weight vector minus the magnitude of the MA vector, the net force vector. All right? So I'm pretty much done now, dude. I can set this equal to that. Okay? And for fun, I'm just going to skip a bunch of steps, and I'm going to show you what happened in period 6 today, which I thought was like kind of beautiful. They did all their stuff with the vector sum diagrams, and they're like, okay, their final solution when they solved for A, they got A equals, and this is the magnitude of our acceleration vector, right? We know the direction of our acceleration vector. For object B, it's down. For object A, it's to the right. So we're not even worried about the direction. We're worried about the magnitude here. And the magnitude of the acceleration vector is going to be like, they said negative. I don't know where they got this negative, but they had negative mass of B times gravity field divided by mass of A plus mass plus mass of B, right? So it looks right, dude. I mean, check it out. I don't memorize the solutions. I look at the logic and have fun with the logic. And this looks right. And the logic leading up to this, I don't know, I kind of zoned out a little bit when they were explaining it, but I seemed pretty good. I didn't check their vector sum diagram that they did this step correctly. I didn't check that as well as I could have, but I was working on it, and it looked correct because the units for mass are kilograms. So the units here are kilograms in the denominator, and then mass of B, that's in kilograms, and then G would be in meters per second squared or newtons per kilogram, same thing. Those are equivalent units. So the units check out perfect. So that was fine. I asked students to actually come up with ideas how they could check this equation, and they said, well, if our gravity field G gets stronger, A will become a bigger number, and that seems to make sense. Okay? Again, I'm not sure what that negative is all about, but we didn't worry about it too much. So again, if the gravity field is stronger, then acceleration should get bigger. So it seems like this is correct. If the mass of B were 0, okay, if this mass of B is 0, then A is 0. Now, that means that you take away this mass. Well, is system A going to have any acceleration? No. So that one checks out in reality. What we're doing here is we're testing our model to see if it works in reality. Okay? This is a really useful thing to do. I mean, this is part of science, is actually testing what we've created. So these two variables do seem to check out. Now, if the mass of A gets bigger, this mass here, shouldn't the acceleration go down? I mean, after all, mass of A is in the denominator. Well, if we make this mass larger, sure, our acceleration is going to be a smaller number. I totally buy that. That works out. And this is what we talked about for a while. Okay? But then, so most of this checked out beautifully. But then a student said, hey, wait a second. What if both masses were 1 kilogram? Uh-oh. Now I messed this up. The group that presented this problem actually had a minus here. Mass of A minus mass of B. That's what they had. Okay? So if the masses were the same number, the entire denominator becomes 0. It's called blowing up an equation, because if the denominator becomes 0, the entire fraction is essentially infinity. Okay? It's called blowing up an equation, because the equation becomes infinity. It becomes impossible to solve. Blowing it up. And in real life, you could easily have a 1 kilogram mass here and a 1 kilogram mass there. It's like no big deal. It should still work out. So reality, it works. For our equation, it don't work out. That means something's wrong with our equation, for sure. It's not major, because almost everything checked out. We're definitely close. And so I'll finish working it out so you can see. I'll move this off to the side so you can see what the error actually was. So it's like, that's what they had. And this is an awesome group. They did a great job. Making errors like this are a natural part of learning. I made errors like this for years, and I still make errors all the time. But it's beautiful if we can help you develop strategies to check yourself and be able to really reduce the errors you make. And I think that technique of actually checking your equation is an extremely powerful one. Mass of object A times its acceleration has to equal weight of object B minus mass of object B times acceleration. Right? I just copied this. I just set my tensions equal to each other. So then I get mass of object A times acceleration plus, there's a plus, plus mass of object B times A equals weight of object B. Okay? And then so the acceleration can be factored out, and you have mass of object A plus mass of object B, right? And that's equal to the weight of object B, which is basically the mass of object B times the gravity field of the planet you're on, the gravity field strength of the planet you're on. And then you could divide by mass of A plus mass of B. You divide both sides by that. Okay. On this side, this divides into this to make 1. And you get an acceleration of mass of B, G, divided by mass of A plus mass of B. And I actually know this is correct. Makes perfect sense. One of the things you can do to check it, now it doesn't fail the test when the masses are equal. When mass of A and mass of B happen to have the same mass, the equation doesn't blow up, and it'll work out fine. I'm also sure this is correct because I have some other strategies of checking that I'd like to share. One other thing you can do to check your equations is sometimes you can find a solution by choosing a different system, okay? And another way to solve this problem is to make system A and system B together, combine them, okay? So literally saying, oh, all of this is my system now, okay? And that's kind of interesting because now we have a total mass, right? I'll call it mass total, which is mass of A plus mass of B, right? And the only force acting on our system is the weight of object B. Actually, that's not true. Object A has weight, but it also has a normal force that adds to 0. All right? So what we have then for our vector sum diagram, and this is a little weird, but we have weight, we have normal force going up. I'll do my force diagram first. I got normal force going up. I got the weight of object A going down, but I also have the weight of object B going down, right? So, all right, weight of object B. And if I do my vector sum diagram, normal force is going up, weight of object A adds to that to make 0. So I got normal force, weight of object A, and then I got this extra vector going down, and that's the weight of object B, right? And if I draw a new vector, I should have made that blue. My bad. I'll fix that because I'm adding 3 vectors here, right? So this is the weight of object B right there, because that's also acting on our system. And tension is internal to our system, so we're not really worried about that. So now I've got a net force vector down on our system. Okay. And that is exactly equal to the weight of object B, right? So this is mass total, because now our system's combined, times A, right? And you can see from my vector sum diagram, whoops, you can see right here that the magnitude of the weight of object B has to equal the total mass times the acceleration. And so therefore the acceleration has to equal the weight of object B divided by the total mass. Oh my gosh, this is identical to that. So if I combine system A and B into 1, it still works out. It's a little tricky, the logic, but I get the same exact thing. So, you know, the odds that there's something wrong here at this point are like 0. It's got to be correct. I can't imagine. I can't find an inconsistency. I invite anyone to find an inconsistency because then it's got to be wrong. But that's how few people really check stuff in real life, and I hope you adopt that strategy and give it a shot. That's the best way to get good at it. And thanks for watching. Good luck on the problems. And number 3 and 4, really important problems. I'll talk more about that later. It's definitely going to be on your celebration. Anyway, have a good day. Thanks.